Okay, let's see. The first thing that we want to discuss are frequency distributions. Okay, I didn't cover at all last week's concepts because I'm pretty sure that everybody knows what are the centers of measure and the centers of dispersion. I also shared with you a link with the previous presentation that I had given on the very, very basics concepts. And one thing that I want to make sure that we understand, and we will discuss it actually next week, where we will wrap up distributions and measures of center and dispersion, is how do we choose actually what is the proper measure of center for each one of the data sets. So, for example, sometimes we focus on I'm sorry, on mean. Sometimes we focus on median. The rule of thumb is the following. Do we have outliers? If we have outliers, then we choose the median. If we don't have outliers, usually we go with the mean. Okay, that's the rule of thumb, but there are some exceptions. There are some cases where we need to use mean even if we have outliers. Frequency distribution. What is a frequency distribution? Well, first of all, what is a distribution? The distribution is how our data are distributed over a specific range. Now, when we talk about frequency distribution, what we are looking at is what are those neighborhoods, if we look at it as a network, what are the neighborhoods in the range where we have higher or lower concentration of data. So this is basically what frequency distribution is. So assume that I have a set of grades for a specific test. Let's say test 1, right? For our class, we have 25 students. The range for grades is from 0 to 100. I may end up having 10 or 15 students get a 75. So this will give me the frequency for the specific value for my variable, that are the grades. The value of 75 will have frequency 15. This is basically what frequency is. How do we calculate frequency? How do we create the frequency distribution? How do we analyze it? How do we present it in a visual format? This is what we will be focusing right now. Right here, we have, again, a set of data. And we see on this second, right here, on this third column, the frequency of the data points for each one of these classes. These are the classes, so the range, let's take again the test and assume now that the maximum grade that the student can get is 30. So we have grades from 1 to 30. Okay, and I have a total of students in the class. If I want to know how many students I have in the class, I have to add all those values. So 5 plus 8 plus 6, 19, 27, 27 and 9, 36. So I have 36 students in the class and they received specific grades. They received specific grades. 5 of them, they received a grade between 1 and 5. 8 of them, they received a grade between 6 and 10. 6 of them between 11 and 15, and so on. Now, what are classes? Classes are the way that we split the range into pieces that they have the same size, all of them, and they never overlap. We call them either classes, intervals, sub-ranges, or bins. It really depends on the software that you are working with, or if you're not working on a software, the book that you are reading. The frequency F is the number of data points in each one of the classes. Something that is extremely important is to decide how you will construct your classes. This depends on many things. First of all, it depends on how big the range that you have is. Like if I have my grades fit between 1 and 30, it would make sense to have 30 different classes, because this would assign one grade to each class. But if I have, let's say, the price of, let's say, car prices, right, that they range from $10,000 up to $290,000, then again it would make sense to have probably less than 30 classes, because if I had less than 30 classes, then I would have to put together a car that costs $10,000 and a car that costs $30,000. That although a 20,000 difference for a car price wouldn't make much difference if we are talking about the upper tail, meaning between 270 to 290. I would assume that the frequency there would be 2 or 3, not more than 3 cars are their prices are this high. If we're talking about the lower tail, between 10,000 and 30,000, we have a lot of cars, and we have cars from different categories, and cars that they are targeting different consumers. So what does this mean? This simply means that the number of classes, it really depends on the type of problem that you want to solve. What it says here, that is usually between 5 and 20, is not true. It really depends. It depends on the range. For a regular situation, not for somebody who is a data analyst, yes, that's true, between 5 and 20. But for a data analyst that he works with an abundance of data, thousands of data, and many times the ranges of the data points is huge, then the number of classes, it really depends on two things. How many outliers you have, because sometimes outliers affect how many classes you want to divide your distribution. And also it depends on another factor, and this factor is how many data points you have within your range. Because if you want, let's say, to focus and see smaller subsets of data points in your range, but your range is between 1 and 30, then yes, maybe you want to split the classes of size 2. So you will have 15 classes there. Let's see now how we find the class size and what are specific requirements for the classes. The first requirement for the class, for the classes that you are working with, is that they should have the same size. All the classes should have the same size. And the next is that they should never overlap the one with the other. Assume that we are working with GPS navigators, prices of GPS navigators. We have 30 of them. And the first thing that we want to do is to divide them into classes. Right here it says that I want to divide them in 7 classes. Now you will say, why 7? What's the reason for 7? Well, there is a very good reason actually, and I don't know if you are aware of that. 7 is a number that when we don't have any other reasons to limit us on how we want to divide our classes, then 7 is a good number. Why? Research has shown, for example, I'll give you an example. Research has shown that if you give surveys, the best number of ratings that you can give in a survey is 7. Although most of surveys have either 4, 5, or 10 differentiations, different inputs that you can give, from very dissatisfied to very satisfied, the best number is 7. This number, it is explained with algebra. We are not going to get into the reasons that they are behind this 7, but it has to do with modula. The number of subclasses right here is 7. So We have 30 data points. We have the range that goes from 59 to 450. These are the prices. We want to find out the class width. So the class width should be the range divided by 7. So 399 is maximum minus minimum, divided by 7, 55.86, rounded up to 56. Now, how do you construct the frequency distribution by hand? You would never do it, but let's make sure that we know how to do it. You construct the lower limit. So you start from 59 because 59 is the lowest price. You add 56, that is the class width, and so on, up to you reach the higher lower limit for the highest class. And then you do exactly the same for the upper limit. One thing that I want you to make sure is that to get the upper limit for each one of the classes, you take the lower limit of the next class and you subtract 1. Remember, you subtract 1 because you don't want to have classes that they overlap. The reason that we don't want to have classes that they overlap is that if the first class is between 59 and 115, and the next class is from 115 to 170, then if I have a GPS system that costs 115, I don't know in what class to categorize it. So I want to have a unique way of categorizing my data points. Then you take all these values, the prices of the GPS right here, and tally them, count them in the different classes, and find the frequency for each one of them. The midpoint of the class is the lower class limit, the upper class limit divided by 2. The midpoint of the class is important if we create either a relative frequency graph or an ogive graph. We will talk about this in a minute. But it's something that it doesn't sound important. It is important though, especially when we don't have discrete values, but we work with continuous values, then it is important to have the midpoint of a class, especially when we have huge data. We are focusing on these numbers. Now you will tell me, am I going to find midpoint for each one of the class, or am I going to calculate the frequencies by hand? No, of course not. You are going to use an R function to do that. Not only that, but the process that I'm showing you right here is the right process that gives you exact numbers, precise, not approximations. The truth is, when you're working with huge amount of data and you want R to find the frequency distribution, you want R to find these answers today, not tomorrow. Especially if you're working with big data, connecting your R program to Hadoop and downloading millions or billions of data, you definitely do not want exact answers. You want approximations. So in order to do that, you are going to use decriminalization of the frequencies. There are many different methods to do that. So basically, what are these? These are algorithms that allow you to approximate and not give exact frequencies for the different classes for a frequency distribution. And R has different methods of doing that. Since this is not covered in black and it is not covered in Wilcox either, we are not going to be covering this in our class, but you will be using it later. So I'm going to give you a program in R to see how to apply it, and I'm going also to give you a handout explaining you what are these methods, how they are used, and how they differ, the algorithms differ the one with the other. You will find this in the handouts for Sync 2, Week 2 recordings. What is a relative frequency? Well, the relative frequencies are extremely important, and I'm very serious about that. They are extremely important because the relative frequencies are nothing else than the frequencies that they correspond to probability distributions. So this is something that you really want to understand. Relative frequencies are the frequencies over the total number of data points. So if I have in one class right here between 59 and 114, 5 GPSs that they have prices there, I don't care for how many I have, I care about what is the percent of those GPS that they are in this specific class out of all the GPS in my sample. And this is 5 over 30, that is 0.17. Now 0.17 is the relative frequency, but at the same time is the proportion of the class size, of the class frequency over the entire data set. Or if you want to describe it in another way, is the probability that if you choose one GPS out of the entire data set, this GPS will have a price that will fall in the specific class. Okay, so there are many different ways of expressing what relative frequency is. We are going to review this again in week 4 and again in week 5. We are going to see relative frequencies as probability distributions now. So instead of having frequency distribution, we will have probability distribution, once for the discrete variables that they take values 1, 2, 3, 4, and once for continuous variables that they follow the normal distribution. Cumulative frequency. Cumulative frequency is nothing else than the frequency of a class from along with the frequencies of all the previous classes. Important? Well, the relative cumulative frequency, and let's look at this closer. Here I have 3 classes. In this third class, the cumulative frequency is 19. Now, if I consider the relative cumulative frequency for that one, it's going to be 19 over 30. That is something like 60%. What is this? This 60% is the probability that I choose a GPS that has a value, a price between 59 and 226. And what is this? This is the probability if we're right here, we are talking about a specific sample that doesn't probably follows any kind of distribution, specific distribution. But if my sample follows, let's say, the normal distribution, then this would mean the area under the bell curve that falls at a specific x. So if we find the z-score for this x, we will be able to calculate the probability. For those of you that you didn't understand anything from what I said, it's fine. For those of you that you already know some statistics, you realize that the relative cumulative frequency is nothing else than what the z-score table includes, has under it. So, altogether, frequency for the class. First, we have the classes, the frequency for each class, the midpoint for each one of the classes, relative frequency that gives us the probability that each one of these points falls in each one of these classes, cumulative frequency that basically it gives us a probability for all the previous classes. Any questions up to here? Now, if we have 30 points, it's easy by just looking at the points, by just looking at the prices to actually find the mean, find the median, calculate them, know what are the quartiles, what are the percentiles, and so on. What happens though if we are working with thousands of data? Definitely we want to be able to visualize our data. How do we visualize frequency distributions? With histograms. Do we use histograms in data analysis? Every day. Do we use histograms even if we have continuous variables? Yes, we do. Because even if we have continuous variables, we want to be able to split into classes and look at different sampling distributions that they will themselves give us histograms. So are histograms important? 100%. So I want to make sure that we understand what are the histograms and how we create them. Class boundaries. The numbers that separate the classes without forming gaps between them. What are the class boundaries? Well, the class boundaries are nothing else than the gap between the two classes. If I have a discrete variable right here, for example, I have the GPS prices, that the GPS prices are specific dollar amounts, 59, 114, 170, and so on. This never happens in real life. You will always go to a store and they will tell you 59.99 or something like similar, or 59.5, okay, and so on. So it is possible by looking at your data, one of these data points doesn't fall in any of these classes. It falls in between the classes. What do you do then? Okay, this is the reason why you create class boundaries. The class boundaries are extended, let's say, limits around the class, created in such a way that they do not leave any space for any data point to fall in no class, to fall into the to a black hole. Okay. So if you want to create the class boundaries for these classes, you go half under the lower limit and half above the upper limit. So now you go between 114.5 and 114.5. As you can see, these two numbers overlap. Yes, they do overlap, but they are in the class boundaries. The actual class is 114 and 115. So what happens if a value is 114.5? Your choice. You choose where you post. Have you seen this before? 100%. You have seen this before. There are professors that, as you know, all the grade scales in all the universities, our university as well, they say that, let's say, from 80 to 83 is a B minus, from 84 to 86 is a B, from 87 to 90 to 89 is a B plus. Perfect. What happens if you get 83.5? If you get 83.7, what exactly is happening? Oh, well, if you get 83.7, you may assume that you need to go to the higher class. But that's not true. And we will discuss about that in the binomial distribution. It has to do with the decision of the professor of how is he calculating the actual class boundary. The class boundary right here, the simplest way of calculating that is the one that you see. So if you get 87.5, then you should, 86.5, then 86.7, you should get a B plus based on the greedy way of calculating the class boundaries, the one that you see right here. What happens if you get 86.5 though? That's the decision of the professor. He may take you down or he may push you up. Why? Because as you can see, that's the reason. As you can see right here, this is a class boundary for both classes. It doesn't belong to any class. It is in a white space, in a black hole. And as you can see right here, we can create the frequency histogram based on the information that we have seen up till now. What I want you to see in this histogram is that on the x-axis, I have the range of the prices. So from 59 up to 459, something like that it was. I split it into 7 different classes. The class limits are the ones that they include each one of the columns. Right here, the numbers that you see are the midpoints for each one of those columns. The y-axis gives you the frequency number, how many different GPS navigators have prices in each one of those ranges, in each one of those classes. And this is how you create the frequency histogram. This is what the frequency histogram is. Now, for those of you that you have some knowledge, if instead of having the frequency number of GPS navigators here, you had the relative frequency, then these numbers would be, instead from 0 to 10, the y-axis would be from 0 to 1. And the height of each one of these columns will correspond to the probability or to the proportion of the number of navigators that their price fall in each one of the classes. So it will be 17% and 20% and 18% and another 17% and 5% and 2% and so on. And if you add up all those, all of this will give you 100%. Why am I saying that? I say that because I want you to understand, for those of you that you really know probabilities, that this is nothing else than a probability distribution graph, as long as the y-axis represents the relative frequency instead of the actual frequency. Right here, what we see is the same kind of histogram. The only difference is that we are considering the class boundaries for each one of the classes. One thing that I want you to also see here is the x-axis. And I'll ask a question. What's the difference between a histogram and a bar graph? Who knows? Bar graphs on the x-axis have qualitative data. Histograms have ranges of data. So quantitative data, they're going to be the prices. So what do you see here is a bar graph. What do you see on the x-axis? The x-axis has qualitative data. In a bar graph, in the x-axis, you may see fruits, you may see animals, you may see employment occupations, you may see time, months, anything, but you will never see a range. These are not ranges. These are not classes. Also, the bar graphs have gaps in between because the categories, the different categories, because we're talking about categorical data here, they have no connection with each other. That's why we don't make the bars to collapse, to be the one next to each other. In a histogram, especially when we create histograms for variables that they are not discrete and that they are continuous, we never have gaps because they are connected because of the class boundaries that we add in order to correct. Basically, it's a correction of the limits of each one of the classes. Okay. Otherwise, the y-axis is the same. It's a frequency. It's a frequency of data points for each one of the categories here, while for the histogram is a frequency for the is a frequency for each one of the classes. As I said before, we can, and many times we do, we can have a histogram as a behind picture, and we create curves or line graphs around that histogram. A frequency polygon is a line graph that emphasizes basically the midpoints for each one of the columns. So what you see right here, those points that you see right there, are the midpoints for each one of the columns. So if you look at your midpoints, 86.5 and so on, this is how you create the frequency polygon. Now, do you ever create frequency polygon? The bell curve. For those of you that you remember what is the bell curve for the normal distribution, The bell curve is the curve. It's not a polygon because we don't have a discrete variable to work with. We have continuous variable. So that's what makes it a curve. If you think, though, that you are working, let's say, with binomial distributions that we try to approximate by the normal distribution, then you end up having specific histograms. If you take for each one of the classes in the histograms the midpoints and you connect them, you are going to get a polygon that is very similar to the curve, but it has some angles. So right here we see the relative frequency that I was talking before about that. So look at the y-axis and see the difference right here. It goes from 0 to 0.30. Can you make a note and remember that for R test 2? For the R test 2? Okay, there is a problem there, and it's problem 4, I think, that half of the class makes a mistake on. Instead of creating the histogram for the relative frequency, that at that time is going to be presented to you as a probability distribution, you create the histogram for the frequency, and you make a mistake on that one. So the difference between the two histograms is only the y-axis, that each one of the columns shows you the proportion of the data points over the total data points instead of giving you the frequency, the number of the data points in each class. The Ogive graph. The Ogive graph is nothing else than a always monotonous increasing line that basically what it does is it displays to you the cumulative frequency. So if the frequency here is 5, then it's going to be 8. 8 plus 5, it goes to 13. 13, and if this is only 7, then 13 plus 7 is going to 20, and so on. It's a cumulative frequency. That's why always it will be an increasing monotonous curve. And this is an explanation of how to create an Ogive graph. We are not going to go through that in detail. Stem and leaf plots, I'm not going to discuss this. I'm pretty sure that you know them. Data plots are very similar to histograms, basically. The only difference is instead of creating classes, you are considering each value in your range as a class. So you don't create classes, you take the entire range and you take whatever the range is, let's say from 21 to 45. 45 minus 21 gives you 24, so you are going to have 24 points. And you find the frequency for each one of those values. And this is how you create that. If you want to name it, it's like a very, very detailed histogram. Pie chart, we know how to deal with pie charts, but apparently, as you will see in the misuse statistics, Fox News doesn't know how to deal with pie charts. Look at this graph. It's a very interesting graph. Remember, pie chart, if you add up all the numbers, they should add up, all these numbers right here, they should add up to 100%. That's the whole point. In the pie chart, what we see is a relative frequency. Pareto graphs are vertical bar graphs. We have the categorical data on the x-axis. The only difference is that we short them from to decreasing order. So we have always the first column to be that one that refers to that category that has the highest frequency going downwards. We can do that only for bar graphs. We can have Pareto bar graphs, but we cannot have Pareto histograms, right? Because the histograms gives you the range. The range has an order by itself. You cannot just move around the classes. So Pareto charts work only for bar graphs. Now I'm saying that because I see this beautiful thing in Excel that creates Pareto histograms. That is unacceptable. Scatter plots. I'm sure that everybody has worked with scatter plots before. Scatter plots are great graphs as long as we know how to read them. One thing that I want to mention at this point is that we have hundreds of different graphs that we can work with. The whole point of a graph is to represent difficult information in a visual way. They need to be clean, they need to be succinct, they need to actually give you the information with a picture. Graphs that they are convoluted, graphs that they are not explained, graphs that they are incorrect, graphs that they have they don't have actual good colors. And I'm not talking about a scatter plot like this that you see on your screen right here, that is a scatter plot of one relationship between two variables. But assume that you have different categories right here. So assume that these are, let's say, what is this? These are the number of stocked shoes, Nike shoes, that a store has for size 7. So this is what it had. This is what it gives you right here. So Nike shoes, we have different styles, and this gives you how many on the y-axis we see how many different pairs we have stocked in the store. Now, if you want to put in the same graph, the size 8, the size 9, the size 10, the size 11, you definitely want to do the same thing, but you're not going to use gray or light gray or white dots, because then it's going to be very difficult for somebody to review the scatter plots. Now, if you believe that there are neighborhoods of your data, the data are concentrated based on the size of the shoes that you store in your store, that you stock in your store, then you may want to use different colors such as red and green and blue in order to show those neighborhoods on your scatter plot. Okay, so are colors important? Extremely important. Is the scatter plot the right plot in order to use, in order to show this information for the specific example that I give you? Not necessarily. If I have a huge store that has shoes of all the kinds and they make sure that everybody they are stocked up for every size of every Nike style that they have in the store, then this is going to be a mess. But if I have a small store that concentrates on the neighborhood and focuses on the styles that the customers from the neighborhood will come, I may end up having some neighborhoods here that the scatter plot is the right graph to use in order to show that. So if I have realized that there is some kind of network in here, some kind of neighborhood in my graph, then the scatter plot is the right way to present it. Let's assume that we're talking about strategies in, let's say, finance, and different type of means for funds from different strategies and different managers on different funds. Do I want to create scatter plots? Yes, usually when we want to look our results over a peer group, we do use scatter plots. If we have many peer groups, many strategies for an example like that, then we may want for each one of the strategies to, for each one of these peer groups to use a different color. Okay, so yes, scatter plots are helpful for something like that. Although usually we give this information with histograms, many times scatter plots are extremely helpful on describing this type of information. This is a bad scatter plot. Look at it. What does it? What is the example? The example is the iris data set. Okay, so I have the iris data set, and I have how many different iris here? I think I have 3 species of iris, and the petal lengths. This scatter plot shows me the relation between the petal lengths with the petal widths. Okay, so and the x-axis I have the petal length, and the y-axis I have the petal width. Do you see right here 3 different species? The colors supposed to be black, dark, gray, and light gray. As you can see in this scatter plot, immediately the scatter plot has a problem. I cannot see which one is in what category myself. I don't know about you. Is this the only problem that I see in this scatter plot? Well, as a graph, yes. Basically, this is what I see. Otherwise, is a good graph. It's explained nicely, the title is correct, and it shows me what it is. The one thing that I don't see in the actual graph, is a legend to explain me which color corresponds to which species. So this is something that is missing. The colors are bad because they don't give me any information about that. So immediately this can be categorized as a bad graph. Now, if this scatter plot gives me a lot of information about this iris dataset, now as an info, as a type of information that this gives me, I would say that it does give me some information, some important information, and I will tell you immediately what is the information that I see right here. Between 20 to 30 millimeters of length, there is no width. What does this tell me? Since we're talking about iris, flowers, I would expect that if I have a scientist who keeps track of those, of the way that the iris becomes bigger, increases in length and width, I would expect to have no gap right here. What is this gap? By looking at this, immediately I can see that this gap means that I have bad data. What happened right here? I have no idea. But since I jump from length 20 to length 30, what I would assume is that the scientist took a break, had vacation for a long time. That's why he hasn't recorded any information at this point. Otherwise, it cannot be explained that there is no flower of any species, unless if this is some kind of magical situation that made the flowers to jump from 1 minute to the other, from 20 to 30 to length 30 millimeters. Time series, we're not going to talk about time series, although beautiful, we're not going to use them at all in our class. These are the measures of central tendency. You already know that. We can review them really quickly. We are not going to go to any depth. You already know what the mean is, what the average is. But I have to ask you, what is the average? What is the mean? The mean is the value that balances the entire data set. That's why we call it the center of the data set. What does it mean that it balances the data set? It means that if you have a data set, let's say, with 1,000 points in it, the mean is this value that if all the points were the same, then the entire data set would give you a sum that it would be equal. Does it make sense? It's the balancing value. That's why we call it the center of the data set. So if I take all these values right here, that they are the prices of the round trip flights, and I find the mean with the way that you find it, then if I replace each one of these values with the mean, then the data set that I will create, that it will have 7 data points, but each one of them will be the same with each other. It will have the same measures, pretty much, and it will have the same sum also, if you add them up, with this data set that you see in your screen. So the mean is a magical value, is a value that balances all these numbers that they jump up and down. The mean is the value that is in the middle of all these values. And it is in the middle because if you replace each one of them with the mean, what you get is basically a data set that if you add them up all together, they will give you the same number. Now, why is the mean important? Why truly the mean balances? Okay, we can see that it balances like that, but is it always, does always represent the center of the data set? Well, first of all, let's make sure that we see the next slide right here. This is what you do in order to calculate the mean. So if I take the value 527.9 and I change each one of those values with the value 527.9, then basically if I add up those values and I add up this times 7, will give him the same number. So I centralize it. I centralize my data set. But is this, the mean, actually the center for any kind of data set? Well, let's see. Let's look at the median. I'm pretty sure that you all know that the median is the middle value. What does this mean? I take all the values, I put them in order, so I order them, and then I find the middle value. And this is 427. Okay. In this simple example, I want us to see together. The sample mean is 527. The median is 427. Okay, beautiful. I want to buy a ticket. I go to a website and I find not 7, but 107 different prices. I want to get a fair price. If the values that I get, the measures that I get, is the mean is 527 and the median is 427. Both of them basically are the centers of my data set. Which one is correct? Because not both can be, both of them cannot be correct. One of them is correct. One of them represents the center of them. So if I buy a ticket that costs $530 and the center is 427, I overpaid $100. Now you may say that that's not important. Yeah, maybe this is not important if I'm talking about one ticket that I will buy once in my life from the specific data set. But what about if you work, let's say, in a trading room and you bid and you either sell or buy stocks or options every day? At every point at your trades, you want to know what is the center of the prices. you definitely do not want to overpay. And if you calculate your measures, you will come up with a mean and you will come up with a median. What about if they differ? Which one do you trust? So this is very serious. This is very important to know which value we trust. Both of them, they claim to be the centers of a data set. The truth is that for some data sets, we should focus on the mean and we should trust the mean. On some data sets, we should focus on the median and trust the median. When do we trust what? Well, the mean is affected tremendously by outliers. As you can see right here, I have 1, 2, 3, 4, 5 different prices that they are very close to each other. 432, 397, 427, 388, 397. If you look at these 4 values, you will see that the average of those 4 values is around 420 or something like that. You can see that the mean for the 4 values is around 420. But the mean for the 7 values, for the 6 values that you have here, 6 or 7, am I missing something? Right, I have 4 values, 430, these ones, and this, that their mean is around 420. And then if I take this and that in consideration as well, the mean jumps up to 527. Huge difference. And it is a huge difference because only 2 out of 7, and 2 out of 7 is 20% of the values that I have right here, they make the price jump by 33% to 25%. So what happened? Well, what happened is that these values right here, both of them actually, they are very high if you compare them with the others. How high they are? Well, this value right here is almost double the mean of those values, as you can see. This is a little bit lower, but still $300 higher. Are they outliers? Well, we have a very small data set in order to say if they are outliers. But if you have a data set with 100 prices and the 90 of them, they are around 500, and you have 10 of them that they go up to 10,000. And you know what a great example to do that, to work on is go to Amazon and see the prices for our book. There are 2 or 3 sellers that I went there yesterday, and they sell our book for $3,207. If you put all the prices down and you consider those prices as well, the mean value for our book should be something like 1,000. But this is not the average price of the book. So what happened here? Well, the mean that is supposed to be the center of our data set is not. It is not the center of the data set. Why? Because the data set has been skewed because of those 2 outliers, because these are outliers. Even for this small data set, they are outliers. When we have outliers in a data set, what do? It really depends. It depends on the analysis that we perform. What would you do if you go to Amazon to buy your book and you find out that there are sellers right there that they sell it for $3,200? Would you buy it from them? Probably not, okay? Unless if you were desperate. Unless if no one else was selling the book. And if this is the case, then the actual price would be $3,200 and it wouldn't be an outlier anymore. So what exactly happens right here? What do? You would probably just drop those prices and you would say, I don't care, they're crazy. This simply means that you drop your outliers from your data set. Okay, so do we always drop the outliers out of the data set? No. What we do with the outliers is that we investigate them and we try to reason why they exist. If there is an important reason why the outliers are there, then the outliers need to be kept in the data set. Still, though, we will not trust the mean of a data set with outliers. So if I want to know the center of my data set, I will go with the median in that case. Always, not always. I'll give you an example on when I don't go with a mean, although I have outliers. I will tell you that. And then I will give you a counter example on the same problem. So what happens here? Two things that I want you to remember. Outliers affect tremendously the mean. If you have outliers, you have to investigate your data points. You have to investigate your outliers and see why they exist. Is there a serious reason why they exist? For example, let me give you an example. A stock. We look at historical data for a stock, and we see that the last, let's say, 36 months, the stock price is 10, 10, 10, 12, 13, 14, and so on, around those prices. While the last 3 months, the price of the stock increased by, let's say, it doubled or it tripled, and now it sells for $40. You look at all your 36 data points. You look at these 3 different values, and you want to know, you want to find what is the mean price of your stock. Are you going to drop the outliers? Definitely not. You need to go and investigate what happened with the company in these last 3 months. And if these values that you see for the last 3 months are prices that they will hold. If they hold, if there is an important reason why this happened, then these outliers need to stay inside your data set, and the mean is correct. It is correct because this is the actual average price for your stock, whatever it gives you, along with these 3 very high stock prices. Why? Because these are not going to go lower if there was a reason why the stock price increased. So you should go with a mean in this case. I'll give you another example. You have a company that sells, let's say, it's a company that you sell a product. And you sell a product, and the company is small, and you have a revenue, and you have, let's say, 10 customers. Out of those 10 customers, the 9 of them right now, because you are just building your company, the 9 of those customers give you a revenue of, let's say, $10,000 per year. So 9 customers give you $10,000 per year. And you have 1 customer, only one, that gives you $100,000 per year. What's the average? What is the center for your sales? Since this outlier, this customer that gives you a revenue of $100,000 per year, is the customer that actually keeps your company alive at this point. And since you are just trying to forecast sales for next year and you have contracts with this specific company for the next 3 years, then this means that this outlier that makes your revenue, the average revenue, jump from 10,000 that it would be without it to 50,000 that is with it, needs to stay in your data set. You're not going to drop this outlier. It's not an outlier. And the measure, the center of your data set is going to be the mean. It's not going to be the median. The median is 10,000. You don't have a company that has a revenue on average on the center, meaning the average, is not going to be 10,000 for a year. It's going to be 50,000 because you do have this customer and you have a contract with this customer for the next 3 years. Okay, so in this case, although you have an outlier, the right measure that you should consider is the mean. It's not the median. Now, counterexample on that. Did you see what happened with Apple and Imagine Now company 2 days ago, yesterday actually? Apple came out and said that it's not going to make business anymore with that company. That company, I think it's called Imagine, the stock price for that company dropped by 75%. So the truth is that this company is the only customer that they have, serious customer that they have is Apple. They don't need anybody else. The outlier, Apple, is the outlier. Their calculations and measurements for Imagine were based on this outlier. But after all, the outlier was the only important data point in their data set that was holding the company together. Apple drops out as a customer for them, the company dissolves. So I think that we had enough discussion between the mean and the median. The mode is the other center of measure of center. We rarely use it. Mostly we use it for categorical data. What it tells us is that you already know what this is what is the data point that appears most number of times in a data set. There are some ways that we use it. Mostly we use it for categorical data in order to see if we have a point, if we have a group, a category that appears mostly in our data. If you use Excel for now, just make sure that Excel doesn't calculate the bimodal and the trimodal set of data correctly. So if you have a situation like this, Excel will give you that we have the mode here is 397, as you can see. But if you have a situation like this, where you have 397 twice and 427 twice, the Excel is going to give you the data point that appears first in the data, and it will show it as a unimodal, as one mode. So be very careful how you handle Excel with mode with Excel. In R, we don't have any problem with that. Just making sure that we know how we call the distribution. Symmetric distribution is something like that as you can see is very similar to the bell curve. Uniform distribution is rectangular, basically equal classes for each one of the different classes. We have the same frequency, and the mean and the median and the mode, usually they are it is symmetric, so it is in the middle of the distribution. Skewed distribution, this is skewed left. When we say that the distribution is skewed, it means left or right, it means where the tail is. So if the tail is left, we have skewed left distribution. If the tail is right, then we have a skewed right distribution. Measures of variance, and these are the only things that I will go over. Variance, measures of dispersion, and we'll talk about variance and deviations only, standard deviation only. The standard deviation, the variance, is going to be nothing else than the sum of each one. What you do is that you take each one of the data points, you subtract the mean of those, and you square that. You take the sum of them and you divide by the number of the data points. What the variance shows you is how dispersed the distribution is. The standard deviation is standardizing the variance. Basically, these two are the same type of, it gives you the same type of information. There are no differences right here as long as the distributions that we are working with, the data set that we are working with, are one population, simple data set. The standard deviation is how we standardize the variance. And by standardizing, if you want to see it algebraically, is that the variance is a two-dimensional variable, while the standard deviation is one-dimensional. So we take the square root of the variance to calculate it. In general, if you look at scatter plots, let me see if I have an example right here. This is how you calculate it. Do I have a scatter plot? I don't have a scatter plot. Forget about the rest. If I have a scatter plot that shows me relationships between an x and a y variable, and the points are moving all over the place, then this simply means that my deviation of the points are deviating a lot from the mean, so the standard deviation will be high. When this doesn't happen, when the points are concentrating in one neighborhood in a scatter plot, then the variance and the standard deviation are low. The standard deviation is extremely important because it affects the rest of the measures in our distribution. Especially when we work with normal distributions, if we have high standard deviation, it increases the margin of errors when we calculate confidence levels. It increases the confidence level. We need to have high confidence level in order to work with distributions that they have high standard deviation. And we are going to work a lot with standard deviation, calculating, analyzing it, visualizing it for different set of data. The one thing that you need to remember for the standard deviation, for those of you that you don't know what it is basically the standardized way to see how the data set, as a group of data, deviates from the mean. So we have the deviation from for each one of the points. That is nothing else than the difference between the point value and the average, the mean. And the standard deviation, we take all together the points. So we take the sum of them. We create a matrix basically of their squares, of the square of their differences. And this is what we are looking into. And we want to see as a set, as a group set, how far they are from the mean. Is the standard deviation affected by outliers? Yes, it is. The standard deviation is affected by outliers. If I have outliers in my data set, then the standard deviation increases tremendously. Also, the standard deviation increases if my range is very high, it's very big. If I have a huge range and I have equally distributed data all over my range. The standard deviation is smaller if I have concentrated areas in smaller ranges.